This is one of a series of lectures from the Further Maths Support Programme for A-Level Mathematics. In the first of these lectures in this series we'll be looking at Edexcel Mechanics 1, and in this one the topic is kinematics. The Edexcel specification says that you should be able to solve problems first of all by graphical methods, looking at displacement time, velocity time or speed time, and acceleration time graphs. In the graphs on the left hand side here then we're looking at what we can ascertain from each of these types of graphs. From displacement, the requirement really is that you should be able to use the gradient of a line to find the velocity. If it's a velocity time graph, then again the gradient, but this time the gradient of the line is giving the acceleration, and also you may use the area under the line. So if we were to find the area in this first part here, for example, this area is looking at the displacement. Acceleration time graphs actually quite rare in exam questions, however sometimes they are there, and you should be aware that the acceleration, the area under the curve, is equal to the velocity. Of course these are really looking at the gradient is the rate of change of displacement with time, so gradient is looking at a derivative. The area is looking at an integral, although it's not until later modules that you may be expected to use differentiation and integration. So it's just purely looking at the graphs using the idea of gradient and area to find the particular values that you need. The second part of the kinematics specification at Edexcel is knowledge of constant acceleration formula. These are the things which are often known as SUVAT equations, and I'll look at those in a little bit more detail in a second or two. But first of all, looking at a question involving graphical solution. So this question is from January 2011. If we're just reading through the question, first of all it talks about a car accelerating uniformly from rest, so starting with 0 velocity, for 20 seconds. It then moves at a constant speed of some value that we're not given, but for that speed it's travelling for 40 seconds, and then decelerates uniformly for 10 seconds until it comes to rest. The motion of the car, we need to sketch a speed time graph and then an acceleration time graph. And once we've done the graphs, we're told that the total distance travelled is 880 meters, and we need to find the value of v. So taking those then one step at a time, the first one, let's look at a speed time graph. So this will be on the first set of axes here. This will be speed in meters per second, and time along this axis of course, and this will be in seconds. Now we're told that initially we have an acceleration from rest, so starting at the origin line, climbing at some slope. We're not really sure exactly what to do on there because we've got an algebraic value rather than a particular value given. We're told, however, that this value should be marked as v. It then continues with a constant velocity, so a constant velocity is going to be, or constant speed, is going to be shown by a horizontal line. This is for 40 seconds, so for twice as long as the initial part of the motion, and then finally comes to rest in 10 seconds. So let's just make that line a bit better than that. If it's 10 seconds, it's obviously a steeper gradient than the first part of the graph. Putting some detail onto that graph then, we should mark in the times that we know. This one here is at 20. Then have a further 40 seconds, so we've got 60 seconds at this point. And the deceleration takes 10 seconds, so after that we're at 70 seconds. So there we are for the speed time graph. The acceleration time graph, well, the first part of the acceleration is obviously positive. So we've got a value of v is the speed that's reached in 20 seconds. So the acceleration must be v over 20, and it's a constant acceleration, so it's going to be a horizontal line. So again, we don't actually know where v is, but let's just mark it in. There's a horizontal line here for our 20 seconds. If we put in a value on there, it's taken v over 20. This is the acceleration. In meters second to minus 2 meters per second squared. Again, on the other axis, time. For the second part of the motion, the acceleration is 0 because we've got constant velocity. Now, let me see if I can show that. I think I'll draw that with a pen just to give you a better idea where we are. But it's coming along this axis here, staying on the axis. And then for the final 10 seconds, the acceleration is now negative, it's decelerating, right? And it must be twice the size of the first one. So we're expected to see a line double the distance below the axis here, and that would then be at negative v over 10. So there we have the three parts of the acceleration graph. In part B of the question, we're told that the distance moved by the car is a total of 880 meters, and we're asked to find the value of v. Now the distance moved is given by the area under the speed time graph. So if I try and indicate that on the up there, what we're saying is that this area here is equal to 880. So in part B, the distance travelled is given by the area under the speed time graph, and the different ways of finding the area, of course, perhaps the easiest is to use the idea of this being a trapezium. So I'll do that. We have 1/2 the sum of the parallel sides. Well, we know that the axis is 70, and we were told in the question that the constant part of the motion was for a time of 40. So those are the parallel sides in the trapezium, multiplied by v must be equal to 880. Well, we can solve that. V is therefore equal to 2 multiplied by 880 divided by 110, which is therefore 16. So we get 16 meters per second for our answer. Right, now looking at how the marks were awarded in that question, there were 6 marks for the graphs, in fact 3 marks for each of the graphs. In the speed time graph there was a mark of B1. There's no method for that, therefore it's just a mark which is given if it's a correct answer. A B1 for the first part of the motion, and then if both parts of the second and third parts are right, then a second B1 was scored. And finally, if you got that, if the axes were numbered, then a third B1 given their numbers on the axes. That would be the V here and the times of 20, 60 and 70. For the acceleration time graph, there were just 3 B marks given for each of the parts of the motion. So B1, B1 and B1. So there's 6 marks, 3 for each of the graphs. In part B, the question, 4 marks available. There were a method mark and a accuracy mark for this equation set up here. So M1, A1 for the equation, and then a dependent method mark. So that meant that you have to have a correct equation in this part to carry on from there. So this was a dependent method mark here, followed by an A mark, accuracy mark for getting the correct answer of 16. Okay, before leaving this topic, just a quick word about the difference between displacement and distance. If we have a velocity time graph, then we said that the area was looking at displacement. Now this means that the part of the graph which is below the axis here is a negative displacement. So what's happening is, in the first part of the motion, the object is moving in a positive direction, but then in the second part of the motion it moves back towards its starting position, so it's moving backwards. So this is negative velocity here. Whereas in the first part of the motion we have positive. Now, if we're asked in a question to find the displacement, then we should treat the two areas as they are. We're actually finding a positive value here and a negative value in the second part of the motion. So they should be subtracted to find the displacement. However, if the question asks for the distance move, then we should add those two areas together. So for example, let's say that in the first part of the motion this was 100 meters, and in the second part of the motion it moved back 40 meters towards the starting position. Then the displacement at the end would be 100 minus 40, which is 60 meters, whereas the distance moved would be 100 plus 40, which is 140 meters. Moving our attention now to the so-called SUVAT equations. So-called because of the initial letters here for displacement, initial velocity u, final velocity v, acceleration a, and time taken. It's useful to have some idea of where the equations come from, So this graph is just indicating that the acceleration we said before is the gradient of the line, and the gradient here we can calculate by the difference in v and u, so the change in the velocity here, this distance is v minus u. If we divide that by time, we've then got the acceleration, so that the acceleration is v minus u over t. This of course leads to the first equation, v equals u plus at. The displacement is the area under the line, and if we treat that as a trapezium, then that is 1/2 of the parallel sides, sum of the parallel sides, u plus v multiplied by t. The other equations come from eliminating v, u and t respectively, so that we get the set of equations I'm sure well known to you, but they should be learned and you should be able to recite them. The important thing to realise is that there are a set of 5 equations, and in each one of the variables that we have is missing, so that there is an equation for every situation. And in exam questions then, what you should be doing is to write down the values that you're given, and then to decide which equation is to be used, and then solving that equation for the unknown quantity. Right, here's a typical equation then with the SUVAT equations. Just reading through the question: a ball thrown vertically upwards with speed u from a point P h meters above the ground. So just drawing a diagram as we do that then, we're starting off at some position h and an initial velocity upwards of u meters per second. The ball goes up and then hits the ground at 0.75 seconds later, so t is equal to 0.75 seconds. And at that point the speed of the ball is 6.45 meters per second. Now of course we're modelling the ball as a particle. We're asked to first of all show that u is 0.9, then the height above P which the ball rises, so we're asked to find this height that it rises to before it starts to fall, and then to find the height h. In part A then we need to show that u is 0.9, so we're asked to find u, that's the thing that we're looking for. We know that the final velocity v is 6.45, but that's in a downward direction, so v is negative 6.45. We know at that point t is 0.75, and of course the acceleration, downward acceleration due to gravity, negative 9.8 is what you're expected to use in Edexcel papers. So we've got v, u, a and t, so we've got the equation, haven't we? V equals u plus a t. Therefore, substituting the values that we know, negative 6.45 equals u minus 9.8 multiplied by 0.75. This solves then quite straightforwardly to u is negative 6.45 plus 9.8 multiplied by 0.75, which turns out to be 0.9, and we know it's units meters per second. In the second part of the motion, if we take its starting position as being 0, so that's going to be our origin, then we know that the final velocity at the top of the motion will be 0. So at the top it stops, so v is equal to 0. We now know that u, its initial velocity was 0.9 upwards. We have an acceleration negative 9.8, and we would like to find the height s above the starting point. Now here we've got v, u, a and s, so we can use v squared equals u squared plus 2as. That gives us 0 is equal to 0.9 squared, and then minus 2 multiplied by 9.8 multiplied by s. And solving that for s is 0.9 squared divided by 2 multiplied by 9.8, which turns out to be 0.041 meters. So the height above its starting point, 0.41. Sticking with the idea that our starting point is at height 0, then we can work out h, because at the end of the motion it will be at a position s is equal to negative h. Now we know the time, t, 0.75. We've got s is negative h, t, 0.75. The acceleration, negative 9.8, and u is 0.9. So here we've got s, t, a and u, so the equation to use is s equals ut plus 1/2 at squared. Substituting our values, negative h is 0.9 multiplied by 0.75, and then minus 1/2 times 9.8 times 0.75 squared. That gives a value of h equal to 2.1. An alternative to that solution there for part C would have been to use again that v squared equals u squared plus 2as, because we knew that v was negative 6.45, so we could alternatively have used v squared equals u squared plus 2as. The marking here is quite straightforward. 3 marks in the first part, firstly for a method M1 and accuracy for this first equation M1A1, and then a final A1 for the answer 0.9. Only 2 marks in the second part of the question, M1 for getting the equation, so actually using the values in the correct equation, so M1 here, and then A1 for the final answer. And likewise in the third part, M1 A1 for this equation, and then A1 for the 2.1. Okay, that's the end of this lecture. There are other lectures available for all of the modules that you might meet, and if you wish for any other information, then the Further Mathematics Support Program can be found at the internet address at the bottom of this page.